Welcome, data engineers. Today, we are diving into one of the most critical optimization techniques in Apache Spark, distributed persistence. Let's get started. Imagine reading a massive multi-terabyte file, applying highly complex filtering logic, and then running a query on it. Without persistence, Spark operates in a completely stateless manner, meaning it literally recalculates everything from scratch for every single query. Distributed persistence, commonly referred to as caching, is the powerful optimization technique of saving the intermediate results of your data frames or RDDs directly into the memory or disk of your worker nodes, which we call executors. Why do we specify distributed? Because the data isn't sitting on one single machine, it is intelligently partitioned and spread across your entire cluster of executors. This means that any subsequent actions on that exact same data are executed lightning fast, bypassing the origin storage. It is critical to understand that caching is a lazy operation in Spark. Just calling the cache method in your code does absolutely nothing until a physical action, like a count or show, triggers the actual materialization of the data. We are keeping the data exactly where the compute happens, avoiding heavy network I/O and saving massive amounts of processing time. Let's walk through this flowchart together to truly understand the architecture of persistence. On the far left, we have our raw data node, which could represent massive log files sitting in a data lake like HDFS or Amazon S3. As that raw data flows through our pipeline, transformations like filtering, grouping, or joining it reaches our critical persistence layer, represented here by the central cylinder labeled executor memory or disk. Now, notice how both Action 1 and Action 2 branch out directly from this persisted layer. This is the core concept. If we did not have this persistent cylinder in the middle of our graph, the arrows for Action 1 and Action 2 would have to stretch all the way back to the raw data on the left. By caching at the executor level, Spark completely bypasses the raw data read phase and the costly transformation steps for every single subsequent action you run. This simple architectural shift slashes your processing time significantly and is the absolute foundation of high-performance distributed data engineering in Apache Spark. So, why should we care deeply about distributed persistence? It ultimately boils down to time and money. In the world of big data, reading from physical disk and shuffling data across the network are the two most expensive operations you can possibly perform. If you are doing iterative machine learning or interactive data analysis where you query the exact same cleansed dataset multiple times, recomputing from the source every time is a massive waste of cluster resources. Persistence solves this bottleneck. Furthermore, Spark's caching is inherently fault-tolerant. If a worker node crashes and a cached partition is tragically lost, your job doesn't fail. Spark automatically looks at the lineage graph and recomputes just that one missing partition from the source. It gives you the blistering speed of in-memory computing combined with the ultimate safety net of automated recovery. By mastering this, you get substantially faster jobs, lower cloud infrastructure costs, and highly responsive data pipelines that keep your downstream consumers happy. Take a close look at this sequence diagram. It clearly contrasts the first action execution with the second. At the very top, when the Spark driver requests Action 1, the executor is forced to go all the way out to external storage to read the raw data. It pulls that data in, applies your transformations, caches it internally within its RAM, and finally returns the result to the driver. This is a slow, expensive round trip. But pay close attention to Action 2. When the driver requests the second action, the executor does not talk to the external storage layer at all. It grabs the data right from its own local cache. That second round trip is incredibly short, cutting out network latency and disk seeks completely. This visualizes exactly why caching is the silver bullet for iterative workloads. You pay the heavy storage I/O and processing penalty exactly once, reaping the performance rewards on every single subsequent query. Now that we understand the why, let's look at the how. In the Apache Spark API, you have two primary methods to save your data state: cache and persist. Think of cache as a convenient, developer-friendly shortcut. When you simply call df.cache, you are actually invoking persist under the hood with a pre-configured default storage level. It is crucial to know that for data frames and datasets, this default is memory and disk. However, for the older legacy RDD API, the default is memory only. But what if you want granular control over your hardware? That's exactly where persist comes in. Passing a specific storage level to persist allows you to explicitly define exactly how and where your data should be stored across the cluster components. Remember the golden rule we discussed earlier: both of these methods are purely lazy. Simply writing df.cache in your script does not put anything in memory. You must trigger a physical action like df.count or writing to a file to actually materialize that cache across the executor network. This diagram provides a clear mental map of the relationship between our two persistence commands. Starting at the top with our data frame or RDD, we can branch left to use the cache function or right to use the persist function. Notice the dotted line leading from cache to the applies default level node. It emphasizes that caching is merely a syntactic wrapper. If you follow the path down, you see the critical architectural distinction. Data frames safely default to memory and disk to prevent aggressive out-of-memory crashes, while RDDs aggressively default to memory only. If you branch to the right to use persist, you completely bypass these defaults, empowering you to dictate the custom storage level. Understanding this API routing is fundamentally crucial for tuning your distributed applications correctly and avoiding unexpected memory pressure on your cluster. Let's dive deep into the core storage levels, which act as the absolute heart of Spark's persistence engine. Memory only is blazing fast because it stores raw Java objects directly in the JVM heap. However, it is risky. If your data exceeds the executor's RAM, those partitions are evicted using a least recently used, or LRU, policy, meaning they must be completely recomputed later if requested. Memory and disk is much safer and is the default for modern data frames. If RAM fills up, Spark seamlessly and gracefully spills the excess partitions to the local disk of the worker nodes. Disk only skips the RAM entirely. While that sounds slow, reading from a local SSD is still significantly faster than recomputing a massively complex, multi-stage transformation chain. The LRU eviction policy is a lifesaver. It ensures your executors don't violently crash from out-of-memory errors. Spark acts as a smart traffic cop, gracefully removing the oldest cached partitions to make room for new, active computations. Let's trace the physical lifecycle of a data partition as it gets cached in real time. We start on the far left with our incoming data partition heading into the executor node. The first decision node asks the critical question, does this fit in RAM? If yes, fantastic. It goes straight to the executor JVM memory. But if the memory is already full, we hit the crucial second decision node, which interrogates your designated storage level. If you aggressively chose memory only, the partition is simply dropped or evicted. It is gone, and Spark must recompute it from scratch if requested again. But if you smartly chose memory and disk, the data spills safely to the local disk. This flowchart perfectly illustrates why memory and disk provides an essential safety net for unpredictable or massive datasets, preventing catastrophic job failures. To truly elevate yourself to an expert-level Spark tuner, you absolutely must understand serialization and replication modifiers. If you append SER to a storage level, like memory-only SER, Spark shifts from storing raw Java objects to storing the data as tightly packed, serialized byte arrays. This drastically reduces the memory footprint, often shrinking the data by 2x to 4x. More importantly, it significantly lowers garbage collection pressure on the JVM, which is a major source of job slowdowns. The trade-off: you pay a small CPU penalty to deserialize the data when you actually read it. What about high availability? Appending 2 to your level, like memory and disk 2, forces Spark to actively replicate every cached partition to a second worker node over the network. If one node suddenly dies, the data is instantly available on the replica, bypassing the need for recomputation entirely. It's a strict trade-off. You are sacrificing double the memory space to gain ultra-fast, zero downtime fault tolerance. This hierarchical tree breaks down our advanced storage modifiers into their specific pros and cons. On the left side, we explore serialization. You can see it converts standard data into serialized byte arrays. Following the arrows down, the clear, undeniable benefit is massively lower memory usage and reduced garbage collection pauses, which comes at the cost of slightly higher CPU usage. On the right side, we explore replication, which physically copies data over the network to two distinct nodes. The massive advantage here is instant fault tolerance in highly volatile clusters, but the glaring cost is that it absolutely doubles your cluster storage requirements. By visually separating these trade-offs, you as a data engineer can make highly precise, calculated decisions based on whether your specific cluster architecture is currently CPU-bound or memory-bound. Choosing the absolute correct storage level is what separates the novices from the senior data engineers. Let me give you the definitive decision matrix. Rule number 1, always ask yourself if recomputation is actually expensive. If it's a fast operation, don't cache it at all, save your RAM. Rule number 2, Try the default first. Memory and disk for data frames is heavily optimized by Databricks and the open source community. If your data comfortably fits in memory and you demand maximum speed, explicitly set it to memory only. However, if you open your Spark UI and notice heavy garbage collection pauses eating up your execution time, that means you have way too many Java objects choking the JVM. Switch immediately to memory-only SER. It shrinks the data and relieves the JVM instantly. Only use disk only if your transformation logic is incredibly expensive, like complex text parsing or machine learning feature engineering, and your cluster memory is severely constrained. Follow these rules, and you will optimize flawlessly. I absolutely love this decision tree diagram because it provides you with a foolproof, step-by-step algorithmic approach for Spark memory tuning. At the very top, we ask the fundamental question, is recomputing this data expensive? If it is a cheap, fast filter, do not even bother caching. Just follow the no path to save memory. If it is expensive, we ask, does it fit perfectly in RAM? If no, we fall back to the safe harbor of memory and disk. If yes, we ask the final expert-level diagnostic question, are we experiencing high garbage collection pauses? If your GC times are destroying your performance, you follow the yes path straight to memory-only SER to compress the data. If your JVM is healthy and breathing fine, you go with memory only. By strictly following this exact chart, you will perfectly tune your Spark memory architecture every single time. Let's bring all this theory into a highly practical, real-world scenario. Imagine you are the lead data engineer tasked with building a massive fraud detection machine learning pipeline. Your job reads a staggering 5 terabyte dataset from Amazon S3. You clean it, join it with multiple dimensional lookup tables, and filter out bad records. This heavy preprocessing phase takes 45 brutal minutes. Now, the data scientist's machine learning algorithm needs to iterate over this clean dataset 100 separate times to train the model's weights. Without caching, Spark's stateless nature means it would reread from S3 and rerun that massive 45-minute cleaning step 100 times. The job would literally take days to complete. But by calling persist, memory, and disk on the cleansed data frame right before the training loop begins, that 45-minute penalty is paid exactly once. The cleansed data sits warmly in the executor's RAM. The 100 milliliters iterations now fetch data in milliseconds, reducing a multi-day pipeline down to under an hour. That is the true power of persistence. This sequence diagram beautifully demonstrates the massive operational power of caching in an enterprise machine learning workflow. First, data moves from the S3 data lake into our Spark preprocessing module. That long, painful 45-minute cleaning and joining step occurs here. But then, crucially, the finalized data is pushed directly into the executor RAM cache using the persist command. Now, direct your eyes to the loop box at the bottom. The ML training loop rigorously requests the data 100 times. But notice exactly where those fetch arrows go. They only travel to the executor RAM cache, returning instantaneously in milliseconds. They strictly do not cross back over to the Spark preprocessing step or the S3 data lake. This complete isolation of the fast iterative loop from the expensive I/O processing steps is exactly how top-tier enterprise teams scale their AI workloads so efficiently. We conclude our deep dive with crucial monitoring techniques and best practices. How do you definitively know if your caching strategy is actually working? You navigate to the Storage tab in the Spark Web UI. It tells you exactly how many partitions are cached, what exact storage level is applied, and critically, if any data has spilled to disk. You must check the fraction cached metric if it is not 100%. Spark is silently recomputing the missing partitions, hurting your performance. But remember, cluster memory is a highly finite and expensive resource. If you cache a massive data frame, use it, and then simply move on to a different part of your pipeline, that stale data is violently hogging precious RAM. Always call df.unpersist when you are completely done with a dataset. This proactively frees up cluster resources for the next stages of your pipeline. Master these persistent strategies, and you'll write incredibly robust, high-performance big data pipelines. Thank you for joining. I invite you all to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. This final flowchart represents your ongoing, iterative lifecycle as a professional Spark developer. You deploy your Spark code, trigger the cache, and immediately jump to inspect the Spark UI Storage tab. From there, you actively monitor the cluster health. If you see a 100% in memory hit ratio and everything is running smoothly, great job. You finish your pipeline logic and responsibly call on persist to clean up your footprint. But if you see massive, unexpected spills to disk or crippling garbage collection pauses, you follow the bottom path. That is your diagnostic signal to refactor your code and tune your storage level, perhaps switching to a serialized format like memory-only SER. Keep this development lifecycle firmly in mind on your daily projects. Please like this video, subscribe to the channel, and check out quicktechie.com to absolutely take your data engineering career to the next level.